So second order measurement systems. We introduced them previously, and we learned how they respond to initial conditions only, right? Free response. Second order measurement systems are subjected to a variety of forcing functions, F, however. So it's not just free response that we care about, also forcing. It's pretty obvious that we care about forcing because the forcing function is essentially what we're trying to measure, right, with our measurement systems. So we had to get there. We couldn't just stick with free response. In this lecture, we examined two common varieties, step forcing and sinusoidal forcing. In what follows, we developed forced response, FO for forced, solutions, which are the specific solution responses of systems to given inputs, and zero initial conditions, which are all initial conditions are set to 0. So we're actually plugging in initial conditions. It's not just the particular solution. In lecture 3.8, a method is presented for combining free and forced response. Essentially, you just add them together and you can get the response. It's called superposition. Yeah. So, anyways, we'll get there. But for now, we'll focus on the forced response. So, step responses first. Step forcing of the form F of S equals KUS. K is a real number, and US is the unit step function. Models abrupt changes to the input or the measurand. The solution is found by applying zero initial conditions to the general solution. If the roots of the characteristic equation lambda 1 and lambda 2 are distinct, the forced response is just that. Still have my parentheses issue. Well, it's actually, they're fine. It's just that when I import it into Illustrator, it can't recognize the right ones. I don't know why. It's pretty weird, but. Oh. But there's one here too. Okay, so this actually looks a lot like the initial, free response, but like with another factor here. It's essentially going, we're defined, it's essentially there's like the free response, but instead of going to 0 from an initial condition, we're going from 0 to some final value. But it looks exactly the same. It's like a mirror image of it. Once again, so here are our lambdas, our roots of our characteristic equations. Once again, there are 5 possibilities for the locations of the roots of the characteristic equation, lambda 1 and lambda 2, all determined by the value of zeta. However, there are 3 important cases for measurement systems, as we found last time: underdamped, critically damped, and overdamped. So those are the 3 we'll consider. Underdamped. In this case, the roots are distinct and complex. So we have this imaginary part, omega d. From equation 322, the four-step response is, wow, and this is the left one that's messed up, is this. The step forced response, once again, if you go back and look at the underdamped case of the free response, this looks almost identical. It's just like 1 minus it, essentially. And with the phase is this. So this is a decaying sinusoid and then some steady state value, some steady state constant. Okay. The response overshoots, oscillates about, and decays to k over omega n squared. And so that's our steady state value, and that's the value it overshoots and oscillates about. So that's the underdamped case. So that example we just did is underdamped. So if we put a step input into it, we would get this response. Critically damped happens when the roots are equal and real. So the forced step must be modified with this extra t value in there, so that's where this t comes from. But once again, pretty much what we saw for the free response. This response neither oscillates nor overshoots, but just barely, right? Just like in the initial condition case. All right, underdamped. Oh, wow, typo. This should be, this is just totally wrong. This should be zeta greater than 1, and it should be overdamped. Yeah, I would call that an error. Yeah. So in this case, for the overdamped case, the roots are distinct and real, given by equation 3.23. The fourth step is given by equation 322. It's the sum of two decaying real exponentials. And if you look, I didn't rewrite this in the case of overdamped. Sometimes people do, and they write it in terms of zeta and omega n, but it's, frankly, it's a mess. And since all the lambdas are real in this case, this form is, I think, easier to look at. So I just leave it like that. Okay. So figure 3.8 displays the four-step response results, actually. And I feel like, there it is. So pretty. Once again, all the time is spent right here. I like these. So, this looks exactly like the free response, but like upside down, right? So instead of starting out at some initial condition and ending at 0, we start out at 0 and we end at some final value. And once again, when the damping ratio's less than 1, we get this oscillation occurring and this overshoot occurring. When zeta is equal to 1, we get this barely not oscillating response, and then if zeta is greater than 1 overdamped, it sort of slowly oozes up response. Ooze. The ooze. Once again, we're using dimensionless time because we're pretty cool. And yeah, so there's kind of like no surprises there, but it's useful to recognize that there are no surprises there. Gives us some confidence. So now we're going to discuss sinusoidal response, which we could talk about transient sinusoidal response, and those of you in mechatronics solved last week's homework with the transient response for a sinusoidal input for a second order system, and it was good times, such good times. But I felt like it would be more useful for me to just deal with the steady state sinusoidal response for this discussion. The book does the same thing. I looked several places and nobody had ventured into the transient response, and I thought, well, yeah, it's probably not that enlightening to do so. So I decided to follow the trend. So here we consider only the steady state response, allowing us to focus on frequency domain considerations. The second order system transfer function found from the Laplace transform of equation 3.11, which is just the input-output differential equation, right? From input u, generating forcing function f equals ku, to output y has the form. So this form here is the transfer function for the second order system. So fortunately, we know what they are, transfer functions. We take the Laplace transform of the input-output ODE, and we can solve for the output over the input, and that's what the transfer function is. And we're actually using it as kind of a bridge to get to the frequency response function, because when we deal with the frequency response function, that is when we're thinking about sinusoidal inputs. And that's what we're thinking about right now. So the frequency response function, h of j omega, is found via the substitution. S becomes j omega, where omega is the input sinusoidal frequency. So I just plugged in S equals j omega into this expression, and the magnitude and the phase are the ways that we usually think about this frequency response function, not as a polar, or we think of it in this polar sense and not in the rectangular sense. So these functions are plotted in figure 3.9 for a range of zeta. Note especially that h of j omega magnitude is near unity, near 1 at low frequency, and it's near 0 at high frequency, no matter what the damping ratio is. And no matter what the damping ratio is at low frequency, this actually eventually approaches 0 degrees at low frequency, and at high frequency it approaches negative 180. And the damping ratio just kind of describes how the shape goes from low frequency to high frequency. And so notice that for underdamped systems, we have this rise near, what is this? This is the dimensionless angular frequency, omega divided by omega n. And at this key looking line here, that's equal to 1. So what does that say our omega is equal to?
Natural frequency at that point.
Yeah, it's just the natural frequency. So this corresponds to the natural frequency. Whenever you drive a system with a sinusoidal input, near the natural frequency, when you have an underdamped system, the output amplitude is going to be higher than the input amplitude. So that's what this ratio shows. So like this goes up to 5. So at zeta equal 0.1, the output amplitude is 5 times the input amplitude. And that's this resonance phenomenon that we're seeing. We're seeing resonance happen there. And that's pretty cool, right? Like we're seeing that resonance. And we can see where it happens and how catastrophic it would be if we excited the system at that frequency. So that's our magnitude plot, which is, I would say, we care like 2 points about this, and we care 1 point about the phase. Just to give you like quantitative assessments of how much we care. So.
What are the points out of?
Out of just 1. So we care 100% about this, and we care 200% about this. I mean, I was imagining out of 3 total. We were just splitting it between the 2. But since you asked, I thought I would. But the relative weighting between 2 and 1, that's clear no matter what the absolute scale is. So there's that. So maybe there's a factor. What I'd say it is the absolute is whatever you feel. But the relative weight of 2 to 1, no matter how many you divide it by, the relative weights are the same. So that's what I would say. Okay, so we've got phase down here. So phase says that when we have this input sinusoid at low frequency, then there's not much phase lag that's happening, right? So if we stay at low frequency, not much phase lag. If we go up here, there's this transition that happens, and at high frequency, there's 180 degrees of phase lag. So if we're doing the input and the output. And remember that in terms of our dynamic error discussion, that's time lag, right, for our measurement. We don't like that. So, I mean, these are interesting in general, but I would say that very clearly, we want to live with systems that have this amplitude ratio of 1, right? That's where we want to be. So we want to end up with systems that are operating in here. We don't like overdamped systems, not just because they're super slow, but also because look at the magnitude. Look at the magnitude ratio at low frequencies. That's not 1, right? You'd have to go to really, really low frequency. This is a log scale, so you can never get to 0 on it. Just keep going down by a factor of 10 forever. It does end up going to 1, but that means that you have to go to very, very low frequencies before these high damping systems have a magnitude ratio of 1.
But
So
conversely, you don't want to go too low on the underdamped scale either, because then eventually you'll just hit that peak where it'll just explode.
right, so you got to watch out for these ones, the underdamped ones, because if you are ever going to be measuring signals out here, you're going to have this amplification, which is not what you want either. There are some situations where you want to have this, like actually the detector, the MRFM detector, having really low damping is really good for picking up a really small signal because you can amplify it with this, essentially. But in most cases, we want to live around zeta equals 1, right? This nice line here that says, oh yeah, for low frequency it's 1, and for high frequency it tapers off, but it gives us sort of the max bandwidth here of niceness. We can be a little on each side. We can be below, which notice that if you look at the time response to just a step, the sinusoid responds for underdamped. It responds faster and faster the lower damping you get. But you get more oscillation and more overshoot too. So it's kind of a trade-off. You want to be kind of near zeta, but if you go a little bit, zeta equals 1, if you go a little bit above or below, you're good. But if you go too far, then you're probably not going to be good. In the time response, we see that, and then also in the frequency response, we see that. Okay, very good, very good. So the phase, similarly, yeah, we talked about the phase. So for for input a sine omega t plus phi into this second order system with this frequency response function, the steady state response can be found directly from the frequency response. So this is like a really key equation in system analysis. It's a way of interpreting the frequency response function. It says if we put in a sine omega t, we get out a times the magnitude of the frequency response function at that frequency. And sine comes out with the same frequency it went in at, same phase, plus some new phase. And I did not mean to write psi there. That was like autopilot, Rika writing something. I wanted to write angle of h of j omega. We often call it psi, but that's no excuse. You guys don't know that, so. H of j omega. The angle of h of j omega. Which is just the phase of h of j omega. So we use the same metric as before, the nearness of the magnitude of h of j omega to unity, the dynamic error. So we want this to be about 1, and so the dynamic error is going to be the difference between the magnitude and 1. So when delta is about 0, that means that the input or the measurand amplitude and the output or the indication amplitude are approximately equal. Note that according to figure 3.9, which is this one, when delta is about equal to 0, which is when h is about equal to 1, the phase lag and therefore the time lag is relatively small, which is ideal for second order measurement systems. So pretty much we want magnitudes near 1 and we want phases near 0. They happen to correspond, which is good. Otherwise, we'd have to trade off, right? We don't have to trade off. We can have our cake and eat it too, as long as we stay in this sort of operating regime. So the type of thing you might want to consider when you're using a second order measurement system is, so what's the damping ratio would be a good question to ask. It's going to give you which of these curves you're on, right? Then you're going to say, okay, I want to be, say, within 5% of unity with my, of 1 with my damping, or with my magnitude ratio. So it defines some bandwidth where, like, you get to a certain point, maybe down one of these lines, and then you say, oh, okay, I've gotten to 5% below, and that's the maximum frequency I'm going to consider measuring with this device. If I need to measure something that's like up here, that's not going to work very well because it's not going to reflect the actual value at that frequency. So it's important to be aware of these things, otherwise you kind of get bitten by them because you don't know what you're looking at on the measurement device. So most of these devices will happily give you a value that's just wrong, and you have to know when it's wrong. Yeah, and I think that is it for today. That's all I wanted to cover today. The homework quiz, I think the voting, when I saw it last, it was heavily in favor of having the quiz on Sunday. So I will put it up Sunday. I might put it up tomorrow, we'll see, and make it due Sunday, but I'll probably just put it up on Sunday. Make it due Sunday. Okay.
Sunday evening?
I'll put it up Sunday day, so that, like, hopefully lunchtime Sunday, and then on